Hello everybody. So today we are again going to start with the new experiment. It is called as critical heat flux. This experiment is related to the boiling. Okay. So what I have drawn here one figure on this paper. So these are called as the regimes of boiling, or this curve which I have drawn here. This is called as the boiling curve. Okay. So first, before performing the experiment, we need to understand the meaning of this boiling curve. This will be discussed by your theory teachers also, but let us discuss it here itself, so that you will be understanding the experiment in a better way. Okay. Now, when boiling takes place, you can observe at home also, it takes place in different phases. At home you can find there is some motion of fluid initially, then there is some formation of small bubbles, then bigger bubbles are formed, and so on like that. Okay. You can observe this at your home also while preparation of tea. Okay. So same thing we are going to discuss that today here. Now here on this x axis I am having excess temperature. I have written a T excess. This excess temperature is nothing but the actual temperature of the heating surface minus the saturation temperature of water or whatever the fluid is there. Okay. Now if water is there, then saturation temperature you know it is 100. That means T minus T sat, that will be nothing but the actual temperature of the bottom of that heating surface, okay, minus the saturation temperature, that is 100. Okay. So we have excess temperature on the x axis, and on y axis we have rate of heat transfer from that heating surface to the fluid. Okay. So and this is the curve which I have drawn here, it is called as the boiling curve. Now initially when the temperature, this excess temperature is between 0 to 15 degrees, okay, approximately 15 degrees. That means the actual surface heating surface temperature will be how much? It will be 100 to 115 degrees. Okay. So in that temperature range, you will observe that there is some motion of water from that heating surface. Water starts moving from heating surface. So it can be observed at home also. You have to observe it very keenly and very carefully while preparation of tea. Okay. So then that particular regime, that particular phase, it is called as the convection. Okay. It is called as convection boiling. Okay. Now similarly, like this what we say, I just said it is called as phases, they are actually called as the regimes of boiling. So we have different regimes of boiling here. Okay. So the first regime of boiling, it is called as the convection boiling. Later on what happens is, you will find out some small formation of small bubbles is there on the surface, heating surface. Okay. These small bubbles, they are called as nucleates. Okay. They are very small. Okay. Very small bubbles are formed like this. They are called as nucleates. Okay. Now what happens, these nucleates they start rising up through the fluid. Okay. Now they start rising up, and before they reach the free surface of the fluid, they get condensed in between, because the temperature of water closer to the free surface, it is very less, and that is why these bubbles, they get condensed in between. Okay. Now this particular region of boiling, it is called as the subcooled boiling region. Okay. Subcooled boiling region. Actually this subcooled boiling region, it has many significance actually in industry also. So that will be discussed again by your teachers. Okay. And later on, after that, as the temperature of this bottom surface goes on increasing, excess temperature will also increase, and number of bubbles formed, that goes on increasing. Okay. As the number of bubbles formed, it goes on increasing, these number of bubbles or these nucleates, they come together and they form a bigger bubble. Okay. They form a bigger bubble. Now this bubble, since it is bigger in size, okay, and further the temperature of water closer to the heating surface, free surface, has also increased now. Okay. That is why condensation of these bubbles is not possible. Okay. So what is the reason? The size of bubbles is now bigger. Second reason is the temperature of water closer to the free surface is also higher, and that is why these bubbles, they don't condense in between. Okay. Now at home you can see formation of bubbles on the free surface. Actually, in the layman's language, we say that boiling has started. Actually, boiling starts a lot before that. Okay. But during this particular region, which is called as the nucleate boiling, during this particular region, the heat transfer is highest. Okay. And that highest rate of heat transfer, it is called as critical heat transfer rate. Okay. That is why I have called it written here Q critical. Okay. Q critical means it is highest rate of heat transfer. Now, after this, the rate of heat transfer you can see here, it goes on decreasing. Okay. Now, it goes on decreasing. The reason is the number of bubbles which are formed on the heating surface keeps on increasing as the excess temperature goes on increasing. Therefore, a large part of that heating surface is covered now by bubble itself. Okay. And bubble is nothing but it is water vapor, isn't it? And that is water vapor means it has a very low conductivity also, and its coefficient will also will be lesser. Okay. And that is why the heat transfer rate from heating surface to the water gets reduced because of large number of formation of bubbles. Okay. And that is why heat transfer rate goes on decreasing here. Now, here you can see this, I have drawn these zigzag lines. It means that because the number of bubbles which are formed at the bottom surface and number of bubbles which rise up from the bubble, that bottom surface, is not constant. They keep on changing, and that is why the area available for heat transfer at the free surface, it is not constant always. Okay. It keeps on changing, and that is why this zigzag pattern appears. Okay. Now, after this what happens is, again you have almost a straight line here. Okay. Almost a straight line is there at this bottom of unstable region. This straight line is there because now as still the excess temperature goes on increasing, as the excess temperature goes on increasing, number of bubbles formed at the bottom surface, it further increases. So, a time comes when the whole bottom surface is covered by the these bubbles now. The whole bottom surface is covered by the bubbles. So, heat transfer now takes place from heating surface to the bubbles, and from that bubbles to the water now. Okay. So, there is constant heating surface area is available, whereas it is covered by the water vapors, and that is why heat transfer is less, whereas it is constant here for some time. Okay. From here to here, from here to here, suppose. Okay. Now, after this what happens, as the excess temperature further goes on increasing, now radiation comes into picture. Okay. Radiation does not come into picture in this region. Okay. In this remaining region here from this side, because the temperature difference is less. Now, as the temperature difference goes on increasing, radiation also comes into picture, and what happens, because of this radiation, heat transfer again further goes on increasing. Now, heat transfer again increases to some extent. Okay. Okay. But after this, probably there won't be any heat transfer, because the material which is being used for boiling, that may not withstand these high temperatures now after this. Okay. So, now what happens is, in our experimentation we have made use of one wire. Okay. A nichrome wire is there, which is used to where we are going to observe all these regimes on the wire. Okay. So, on this wire now we have to observe these different regimes. Now, I will explain you during the experimentation now, and we will find out this value of critical, Q critical. Okay. So, with this we will pause, we will see the experiment now. Okay. So, this is the experimental setup for the critical heat flux. Again you have this control panel where you can see voltage, current and temperature also. So, here we have a dimmerstat for increasing the supply of this heater. Okay. Now, here you can see this water is there. Okay. And you can see here probably a nichrome wire is there. Now, you can see this nichrome wire like this, isn't it? It is a very, very small nichrome wire. It is 2 mm. The diameter of this nichrome wire is 2 mm. The supply to this nichrome wire is given through this dimmerstat. Okay. So, if I go on increasing the supply of this, if I go on rotating this dimmerstat, the voltage and current flowing through this nichrome wire goes on increasing, and that will increasing the heat transfer rate from the nichrome wire, or rather it will increase the temperature of this nichrome wire. So, as the temperature of this nichrome wire goes on increasing, we will have to observe different regimes which I have just studied, okay, on this nichrome wire. So, I am closing this experimental setup now. Now, as I increase this dimmer stat, we have to observe this value. Okay, so this wire it can be observed from here. So, I hope you can see this nichrome wire, right. So, can you see this nichrome wire? A very thin nichrome wire is there. It may not be very clear, but you will be able to see different, I think. Yes, 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 yes. Now it's visible. Hi. Hello. Increase. Okay. Now we are increasing the heat transfer to this nichrome wire. Okay. So the temperature of nichrome wire slowly goes on increasing. Okay. So initially there will be convection heat transfer. So you will find little motion of water above this nichrome wire. Okay. So you can now see this water has started moving here above this nichrome wire. Okay. So that is called as the convective currents. Okay. These are called as the convective currents. Yes, yes. Now it's clear. Now this wire is clear. Okay. So they are called as convective currents. Now after this you will have a formation of bubbles on this nichrome wire. Increase karo, fast water, speed water, increase karo. Increase kar. Increase it slowly, thoda, little faster. So you can see this formation of bubbles is there now here on this nichrome wire. Now a time comes when the whole of this nichrome wire it is covered by only by the bubbles. That means at that stage heat transfer from this nichrome wire to the water it will be very less. Okay. And later on what happens is this wire cannot withstand that high temperature and it will break. At that particular point whatever the heat is supplied by this wire we call that as a critical heat flux. Okay. So increase it. Yes, now it has broken. You can see here. So what you see here whitish that flow is there, that is nothing but they are bubbles, water vapors are there. Okay. So now at this particular point you can see here the voltage it was 25.2, okay, and the current is 3.71. So 25 into 3.71 whatever the value of wattage will be there, that watt will be there, and divided by the area of that nichrome wire you will get the critical heat flux. Okay. I hope this is clear to you, and still you can discuss that with your teachers also. So these are the specifications. You can just take the screenshot of the specifications also for your calculations. Okay. So with this we will stop here, right? Okay, bye.